Hello everybody, I'm Vasant from Automata Theory and Compiler Design team, and today we'll be discussing a few topics in compiler design, namely basic blocks and flow graphs, optimization of basic blocks, and global data flow analysis. Let's get started. So I would like to start the session by discussing what a basic block is. In this context, I would say a basic block is a set of statements that always executes in a sequence one after the other. So basic blocks contain a set of statements, and the flow of control is from the beginning of the block till the end without any stoppage. There should not be any stoppage for the basic block. Characteristics of blocks. So when we talk about blocks, the blocks have these fundamental characteristics, namely that they should not have any kind of jump statement in between the code of the block. There is no possibility of branching or halting in the middle. All the statements have to execute one after the other in the same order as they appear, and that they should not lose the flow of control. So let's talk about an basic example. So on the left right here, this is a basic block, and this is a basic block because all the instructions are executed in a sequential manner. There's no flow loss. Whereas on the example on the right, this is not a basic block. Why is this not a basic block? Because if you notice line 1, if a less than b go to 4, the flow of control is being shifted from statement 1 to statement 4, and that interrupts the regular flow. And so this cannot be considered as a basic block. A basic block should be linearly executed. We will talk about how to convert this not a basic block into a basic block in the next slide. So algorithms for basic blocks. How do we convert our normal three-way algorithm to a basic block? So if we partition our three address code into basic blocks, we take in input as a sequence of three address codes, and the output we provide is three address statements in exactly one block. So we have two main rules for splitting our code into blocks, and so the first rule is to determine the leaders. Second rule is to determine your base blocks. How do you determine your leader? Well, so to determine your leaders, there's three ways you can determine them. The first way is to identify the first line in your code. The first line is always the leader by default. The second way is to identify a statement that is the target of a conditional. So for example, if I say if condition go to 4, so statement number 4 is going to be a leader statement because that's where the flow of control is being directed at. And the third type of leader is the statement that appears directly after the go to statement. So like I said, if condition go to 4, so the line which comes after this if statement is also a leader statement. So for determining the basic blocks, all the lines which follow the leader, including the leader, is one block. And you always note that the first block, from the beginning of the first statement of the code till wherever it goes, it's known as the initial block always. The first statement is called the first leader, and the first block is called the initial block. So let's look at an example problem right here. So on our left we have our code, and we have to convert this code to basic blocks. So if you see here, the first line, as I said, the first line is always a leader statement. So from starting from line 1, we keep looking, and so 1 2 3 4 5 6 7 8 9 10. Notice how at 9 11 it says if I less than equal to 20 go to 5. Now this is a go to statement, and this is directing us to line 5, which is right here. And as I said, a leader state, the second rule for leader statement is that the go to where the statement where you are going to via flow control is the leader. So in that sense, we have two blocks right here. So namely 1 to 4 and then 5 to 11. Why 5 to 11? Because we are being directed to statement number 5 by statement 11. And we'll form basic blocks, block number b1 and block number b2, as we can see in the diagram on our right. Looking at another example problem, this one is a bit more trickier. So the procedure here is longer, but so let's determine the leader statements first. The first statement I equal to 1, always the leader statements. Then if you go on, look at statement 11 right here. If I less than equal to 10, go to 2. 2 j equal to 1 is also a leader statement because we are going, the flow of controller directs over here. Third statement right here, if j less than equal to 10, go to 3. So 3 also becomes a leader statement right there. Then we keep looking until so if I less than equal to 10, go to 13. 13 statement number 13 is also a leader statement. And now, okay, so now we have to apply the third rule. The third rule states that after every go to line, the next the line immediately following the go to line is also a leader line. So applying these three rules, we know, so we'll have the first block, which is line number 1, because this is the leader block. The second block will be statement number B2 because this is where we are going. The third block will be statement number 3 to statement number 9. Why statement number 9? Because this is the go to statement. We end the block at a goes to statement. Our fourth block will be start at line number 10 and end at line number 11. Fifth block goes at line number 12 only. And our last block will be line number 13 to line number 17. 17 is the end of the code given to us. So okay, now that we know what a basic block is and how to how to differentiate your basic blocks, let's talk about flow graphs. So a flow graph is a directed graph which contains the flow of control information to the set of basic block. A control flow graph is basically used to depict how the program, how the program control is being passed to from one block to the other. And we have three fundamental rules. The fundamental rules here being that the basic blocks we have are the nodes for the graph. The block whose leader is the first statement is always known as the initial block, like we discussed earlier. And there is always a directed edge from block number, let's say block B1 to block B2. If B2 immediately follows B1, it in the given sequence, we can say that B1 is a predecessor to B2. So looking at the example right here, we discussed this example as example problem 1. So we have block B1 and block B2. If you observe last line of, so because we have to execute the blocks in a linear fashion, so we will execute line 5 after line 4, which means we have a linear connection. And at line 11 we have a go to statement, which if I less than equal to 20, go to 5. So from line number 11 we are supposed to go back to block B, to block B2 from here to here, just like this. If you guys, you can see on the right side. This is how you will explain your problem with the help of a flow graph. Looking at another example problem, this is also a code we have discussed earlier. We have split this code into 1, 2, 3, 4, 5, 6 blocks. So if you observe, like I said, the code must execute linearly. So first we will arrange all the blocks in a linear order and arrange them in a linear fashion. Then we look at the go to statements. If I less than equal to 10, go to B. This is go to 30, go to B6. So we go back to this block. And here again, if I less than equal to 10, go to B2. So we will go back here. If J is less than equal to 10, go to B3. We'll go back to this same block right here. This way, we establish the basic flow in our problem right here by using our blocks and the instructions stored inside them. The next topic I should discuss is optimization of basic blocks. So when I say optimization, what I mean to say is optimization is a program transformation technique which basically improves your code by making it faster for the system. So by how does it make it faster? By making the system by making it use lesser CPU memory, by CPU resources, by making it use lesser memory, and it delivers high speed by optimization. So the general consensus is by optimization, a high-level general programming language is replaced by a very, very efficient low-level language which is easily understood by your compiler and your processor. So, and your code optimization should follow three rules, which is basically your output code should not change the meaning of the program which is written initially. Optimization should increase the speed of the program if possible, but not decrease the speed, and it should demand less number of resources. Optimization itself should be fast, and it should not delay the entire program or delay the compiling process. Okay. So how does optimization work? So optimization will be done by the compiler in this context. How it will be done is, in the beginning the user can change or rearrange the code, or use better algorithms to write the code before even before compiling it itself. After generating the intermediate code, the compiler can modify the intermediate code by address calculation and improving loops. So the compiler will observe your code while compilation, and wherever it notices that you can optimize the code, it doesn't need extra resources or certain lines are redundant, it will go ahead and remove them, and this will make your program much more efficient. And while targeting the target machine code, the compiler can make use of memory hierarchy and CPU registers. Now, this concept is basically, it depends on system to system. As we know, like every PC is unique, and so the compiler will process and optimize the code with regards to your system and how it works. Okay. So optimization process can be applied on basic block, as the basic block is basically low level language. While optimizing, we don't need to change the set of expressions, we can use them as it is. There's two types of basic block optimization, which are structure preserving and algebraic transformations. So, giving a brief, structure preserving is basically where the code is the same. You don't make modifications to the code itself, but you remove redundancy in the forms of variables and codes. While algebraic transformation, you change the code itself by removing unnecessary variables and inputting numbers wherever is possible. So in structure preserving transformations, we have four types of algorithms, which are common sub-expression elimination, dead code elimination, removal of temporary variables, and interchange of two independent addition statements. So to discuss them, common sub-expression elimination. Suppose we in this example right here, we have four statements, right? So P equal to A plus B, Q equal to C plus D, R equal to X plus Y, S equal to C minus D. So we have four expressions right here. If you notice, Q equal to C minus D, line 4, we don't need to write S equal to C minus D explicitly, because it's already declared as the value of Q. So instead of writing C minus D here, I can replace C minus D with Q right here. So I can write S equal to Q, and this is much more efficient in terms of in resource allocation for the compiler and for the machine you're using. Dead code elimination is basically where you remove lines of code which you wrote initially, but you just never used. So for example, I have written a code, and in the code I have used certain loops, and after finishing the code in its entirety, I have realized that I don't need the loop at all. I just don't need the extra line. So the compiler understands that these lines are not required, and it eliminates them by itself to reduce the complexity of the program. And by removing these useless things, the code is optimized further. Renaming of temporary variables. So considering the example statement x equal to a plus b, the given statement's value is basically stored in a temporary register, temporary variable x, which can be changed to another temporary variable y. So if I write x equal to a plus b, or if I write y equal to a plus b, both of them have the same meaning. X is a variable, y is a variable. They both have the same value. So I can use x, I can use y interchangeably. There is no need for using x x as it is. And interchanging of two independent adjacent statements. Considering two statements, p equal to a plus b and q equal to x plus y. Notice the first statement doesn't have any relation with the second statement, and the second statement doesn't have any relation to the first statement, which means that we basically write them in the code interchangeably. So I can write p first and then q later, or I can write q first and then p later. It will not really have any impact on the program, and this is more so for convenience and readability of the code. Now let's talk about algebraic transformations. Algebraic transformations, talking about them very broadly, basically instead of declaring the variables and talking like x equal to x plus 0 or x equal to x into 1, we declare the direct numerical value to x instead of writing the entire code. What this does is we don't need to the extra processing power to process the statement x equal to x plus 0. We can just write x equal to x, and that makes our life so much more easier. So if I give my compiler an expression x equal to 5 into 2.7, the compiler has to evaluate 5 into 2.7 and then it will give me the result. Instead of doing that, I can just write x equal to 13.5, and what this does is this makes compilation much more faster and the code will be much more simpler. So talking about global data flow analysis, considering we have learned about blocks and flow graphs so far, what global data flow analysis is basically, so your compiler, when your compiler is you're compiling your code, it looks for ways to optimize the code so that it uses lesser CPU processes and memory allocation. How it does this is it basically looks at the entire code. It processes the entire code and it observes wherever code or variables are redundant, where they are not required and you don't need to process them so far. So wherever it doesn't require them, it gets rid of them. It processes them in a different way, and this kind of optimization, user-defined changing, is basically one problem because the compiler cannot understand user-defined changing. It can only understand the entire flow of control when it reads the program from the beginning to the ending. So taking an example, we have two statements here, x equal to a plus b and x equal to 6 into 3. So if you notice in this code, x equal to a plus b, this statement is redundant. Why is this redundant? Because in line number 2, we are declaring x equal to 6 into 3, which is 18, which means that the value of a plus b is not required. It's redundant. We don't need it. We just never used it in the program. So instead of writing this code right here, I can get rid of line 1 and just get away with writing x equal to 18 instead of writing 6 into 3, because that's going to increase my complexity. So I'm just going to write x equal to 18, and that will just make my program so much simpler, because the processing we needed for 2 lines, we are getting done in 1 line. Let's talk about one more example. So we have a equal to 1, b equal to 2, c equal to 3. If condition x equal to a plus 5, else x equal to b plus 4, c equal to x plus 1. Notice how a, b and c are already explicitly declared, and we have given expressions here, x equal to a plus by and x equal to b plus 4. Instead of writing a plus by, a plus 5, can I write a equal to 1? So x equal to 1 plus 5, or can I write as x equal to 6? I can. That will make my program easier. In the same way, x equal to b plus 4, b equal to 2. So can I write 2 plus 4? I can. So x equal to 6. Notice, so if condition x equal to 6, else condition x equal to 6. So considering that we have the same value of x regardless of the condition, instead of writing this if else, I can get rid of the if else entirely, and instead of writing line 4 and 5, I can use x equal to 6. And looking at the last line, c equal to x plus 1. So we have already seen that x equal to 6 from our previous iteration. So I can use the value of x right here. I can use x equal to 6, and so c equal to 6 plus 1, 7. So here, instead of writing 6 lines of codes, I can basically write 6 equal to 7 and get away with it. This will reduce the load on your computer, and it will make your compiler's job much more easy. This is what the compiler does to optimize your code. Yeah, this is all I would like to discuss for today. Thank you.